Welcome back to our workshop on plant diversity, climate change, and conservation, the view from California. This module will look at landscapes, microclimates, and climate refugia. So in an earlier module, we looked at climate gradients and vegetation in California. And if you looked at these pictures, first of all, I think most of us, or most of you who spent time in natural environments, will say, okay, quite confident that these plants live in different climates, even if you didn't know the particular geography of California, clearly from these tall forests like in the upper left to the deserts in the lower right. And we've been thinking about these very large-scale phenomenon, but for this module, I really want to zero in on the thing that I've spent the most time thinking about in my research, which is what happens at very fine scales within landscapes. You're going to see this picture repeatedly. I use it all the time in my lectures and teaching. It's a landscape in Central California. And here we have just, this is not extreme. This is just a gentle little rolling landscape. But in this case, north is to the left here. So what we have is blue oak woodlands, actually. We've talked about blue oak scattered across these hills. But then there's a little ravine, and there's a small, you imagine there's a small water course running down there, at least some wetter soils. And this hillside, it's just tilted a little bit. You can see it's just sort of tilted a little bit to the left, and it's facing towards the north. So it's cooler. And this community here has some bay trees, some coast live oak, and these are evergreen species that are more characteristic of cooler and moister environments compared to these blue oaks out on the hills. Now, right across the valley on this side is chaparral. This is mostly chamise, and this is a California plant that dominates our shrublands, extremely drought tolerant, very, very flammable. So chaparral systems can be highly flammable. And if you were thinking at a biogeographic scale, you'd think, well, chaparral is more common in Southern California, and these sort of evergreen woodlands are more common in Northern California. But look, here they are, literally touching at the bottom of that stream valley, just meters apart from each other. And it's just reflecting the fact that that chaparral is on a slope facing south, and this riparian zone is facing north and has a little extra moisture, presumably, in that watercourse. So what does this mean for us? What is the significance of this fine scale variation, and how does this play into climate change impacts and conservation strategies as well? So there's actually a classic paper from 1947, but this is going on a gradient from a higher rainfall to a lower rainfall end. And the message of the paper was about how species, whether they live on north-facing slopes or south-facing slopes, depends on where they are along these geographic gradients. So this is this idea that has been, first of all, very well known to every field naturalist and has been in the literature for a long time, but hadn't been discussed a lot in terms of climate change until we've been thinking about it in the last sort of 10 years and even more in the last few years. Okay, so here's a modern version of this pattern. This is a data set that comes from the United States Forest Service. They have put out tens of thousands of plots across the entire United States. It's called the Forest Inventory and Analysis Data Set. It is the most incredible data, and all made available free for researchers and collected on an ongoing basis by the Forest Service. So every point here is a plot. And the size of the point is the abundance of Pinus attenuata, knobcone pine, shown here in the lower left. It's a very fire-embracing pine with these cones that are closed and burst open in fires. So we're not going to talk about fire right now, just talk about where they live in the landscape. And every plot can be characterized in a couple of ways. One is the temperature. So these plots are in the southern and lower elevation end of the range, and these plots are in the cooler and northern end of the range. The y-axis is the plot facing south, or is it facing north? And we can do some simple math with the slope and aspect of a plot that we would measure just with a compass in the field, and turn it into a single number that characterizes how much is it south facing, how much is it north facing. Okay, so what do we see? Think about it going this way. As a species moves to hotter and hotter regions geographically, they'll increasingly shift to the cooler north-facing slope so that the topography offsets the regional climate. So as the species gets to the edge of its climatic niche, it's increasingly restricted to microsites because it's just getting too hot, but it can still hang on as long as it's more on these south-facing sites. And when it gets to the really cool end of its range, where it might be getting too cold for it, where you find it is shifting and just occurring on these hotter south-facing. So you have this trade-off between the regional climate and the microclimate. Now, in my research group, we kind of fuzzed our eyes a little bit and thought about the first principles behind this. And we visualize this as this parallelogram, not just the trend, but the fact that there's kind of an empty corner there, right? So when it's really cold, species need the extra warmth of being on a south-facing slope. So this corner is empty. Then in the middle, they live across the entire top of, the entire landscape. And then you get to the other end, and there's a few points there, but really most of them shift down here. And we've done a bunch of analysis on a bunch of species that support this, the way I've drawn this here for you, that it's really about how there's at the edges, you have this particular, you cut off these corners of the edges, and then in the middle, a species can occupy the whole landscape from south to north. Okay, you take this idea and you go into a community. So now we're going to go to one site on a landscape. And the site I'm going to show you is up in Sonoma County. Each community is composed of some species from warm places and some species from south places. So a community occupies one location along a regional climate gradient. Some of the species in the community are warm adapted species at the cool end of their range. Others are cool adapted species at the warm end of the range. And when we talk about these things, we're always going back and forth, south to north, cool to warm. So I will try to say it really clearly and certainly not make any mistakes on it. So what happens? Within that single community, within one location, sitting in one place on that regional climate gradient, the species adapted to warmer conditions will be found on those south-facing slopes. This actually stands for equatorial facing, because when we publish this in the international literature, to acknowledge that in the southern hemisphere, everything reverses. So south-facing and north-facing reverse. So we talk about equatorial facing, meaning facing towards the equator and towards the hotter conditions. The species from cooler locations we find on the pole-facing, cooler slopes. Here it's north-facing. So the hypothesis here is that the way species are spread out on a landscape actually is an indicator of whether these species overall are adapted to hotter or cooler conditions. And then from that, we have some thoughts about what the expected impacts of climate change may be. So this is work that my lab has worked up at Pepperwood Preserve in Sonoma County for more than 10 years. It's a spectacular research reserve. Every dot here is a different monitoring site for something: weather, trees, birds, wildlife cameras, grassland monitoring, plant phenology. So it's just been, many, many different study systems layered on top. This is about 3,000 acres. So the scale there, kind of 3 miles, corner to corner, about a 3,000 acre reserve. Also burned in the Tubbs fire, and that's a story for another day, although I've been alluding to it. We had the great good fortune to have an experimental, a new technology being developed by NASA that they're developing. NASA flies things on airplanes before they put them on satellites. Matt Clark has a remote sensor at Sonoma State, and he was able to get his NASA collaborators to fly Pepperwood at a low elevation, a low altitude with the plane, to get a very high resolution image with a new hyperspectral remote sensing technology. And from that, and given that we know where a lot of trees live, so we have lots of ground data, we were able to calibrate a map of the dominant tree species and dominant vegetation at about an 85% accuracy. So we can map out where each of the different tree species lives all across this landscape. And then we know, of course, the slope and the aspect and the topography. So a very unusual data set to have such a high density coverage for a lot of different species on this kind of rugged landscape. But this is what's coming in the future, because these technologies are going onto satellites soon. Okay, so from that, we know where species live, south-facing, north-facing, because we know the whole topography of the reserve. Then we step back and we say, how do we quantify where a species lives? We just need a number. Is this a species that lives in hot places or cool places? And we take that geographic range idea, but we do something very simple. This is just to illustrate to you that forest inventory analysis. Every black dot here is a point. This is the density of points the Forest Service has collected in this public data set, private public lands across the entire country. They actually obscure the location because it's very sensitive that they work in private lands. So they provide the data, but they don't provide exactly the location of the plots. But close. Now we see here's black oak, Quercus cologii. All these red dots have black oak. And then here's a climate map. And this is just the underlying mean annual temperature. Again, it shows where all the FAA plots are. So the white spots here mean that there's no trees. This shows all the forest plots. We take the black oak, we layer it on the climate, and we just make a histogram. This is just a frequency distribution. Some of the black oaks live in warm places, some live in cold places. Here's the average. So this is just a simple method that is used quite widely in different ways, just to put a number on each plant, characterize that whole range as a simple number. Okay, when we do that, the first result upholds the basic hypothesis and goes back to that paper from the 1940s. The x-axis is on the right, and I've shifted units a little bit. My x-axis is about dryness here. It's that climatic water deficit I referred to earlier, but just think about it as wet on the left to dry on the right, okay? So, and in each dot is a species. So we have blue oak, we have, these are genus species abbreviations some of you will recognize. We have redwood, we have padrone, and about a dozen species on the pepperwood landscape. The x-axis is, does this species in general live in dry places or wet places? And over here is the dry side. The y-axis is, does it live on south-facing slopes or north-facing slopes? And what we see is, as the species from dry places at a geographic range live on the drier part of the landscape at a local site level. And this is the prediction that we made from that conceptual model I showed you. And if you think about it the other way, if you walked onto the pepperwood landscape, you could look at the species on the south-facing slopes and say, oh, these species are adapted to hotter conditions, and we expect they also are found further south. If you go on the north-facing slope, these species are adapted to cooler conditions, and they're actually also found further north. And actually, there's nothing surprising here to anyone, any field botanist in natural history, but this was really our effort to put some numbers on it and quantify it. But the next step maybe begins to get a little bit counterintuitive. This diagram's a little busy. We go back to our parallelogram of where species live on landscapes. And now we think, what happens when climate changes? Well, climate change is that each side of the landscape moves to the right, okay? The topography is fixed, so sites are equally south-facing, equally north-facing. Climate change doesn't change that. What it does is it moves them towards warmer and or drier. So if we start here, this population is coming up against the edge of its climatic niche. And we would actually predict that this population might be driven locally extinct. This population here, which is tucked up in these south-facing slopes, actually looks like it could expand in the future and expand across the landscape. And we won't, let's not spend time in the middle one. So just like before, so just think, really what I'm trying to get to is, instead of thinking about moving north or moving uphill, we're thinking about, what about moving from the south-facing slope to the north-facing slope? What about moving down into a valley, over to the other side of the hill? A lot of climate change impacts may play out at this very local scale. And this also, as we'll see, gives us some other ways of thinking about the conservation biology. Now, the paradox here, and I'll spend a couple, or not the paradox, but the important thought experiment here is, this species is tucked into a cool location, a pole-facing, north-facing slope. So right now, that looks like a nice place to be protected from climate because it's nice and cool. Our model here says that's the most vulnerable species on the landscape because it's right up against the edge of its distribution. And that's the last place it can survive, and a little bit warmer, and that's it. It can't live there anymore. So we modeled that a little bit more. And again, with these same 12 species, we actually just said, now I'm flipping axes on you, so stay with me. The x-axis now is, does this species live on the south-facing slopes or the north-facing slopes? Okay, so cool to wet, or cool to dry. Sorry, cool to warmer, wetter to drier. The y-axis is a projection from our climate modeling. So now we do a model kind of like the one I showed you about how we model species ranges. Will this species do better in the future or worse? Are the conditions going to be better, be more suitable or more within that envelope of suitability, or less suitable? And as we predicted from this whole model, the species sitting tucked into those little north-facing, cooler slopes are actually going to be doing worse in the future. So those are, whereas the ones on a south-facing slope, which is hot. And I think the reason that maybe this is counterintuitive is what we're saying is the species that occupy the hottest places on the landscape are going to do even better in the future. And the logic behind that is the reason that they're out on that hottest location is this is they're at the cool edge of their climate niche. Because they're at the cool edge, the only place they can live on the landscape is in a hot little microsite that keeps them from being too cold. So as it gets warmer, they're just moving right into the sort of the center of that climate envelope. And I'll give you two examples. Let me give you one good example. Coast live oak, we think of as very common in the Bay Area. It actually barely goes past Sonoma. So Sonoma is the northern end, the cool end of the range for coast live oak. So you find it on south-facing slopes. Well, coast live oak goes all the way to Baja. So as it gets warmer in Sonoma, coast live oak, might be going things are getting better. They're going more towards the middle of its climate envelope. So the one that's out on that south-facing slope now, up at the cool edge of its range, is actually the future winner, and the inverse on the north-facing. So that may or may not be intuitive, depending on how well I explained it and whether my logic as you followed my logic. So this gets to this idea of what is a climate refugium. And I think there's an intuition that species that are in a cool location are in a climate refuge, like a ravine or a north-facing slope, is protected. And what I'm trying to argue here is that it could be exactly the opposite, that they're the most vulnerable, at least in certain conditions. So a lot of people have thought about this idea of what are climate refugia. And probably the best argument for climate refugia are habitats that are built around permanent standing water. So if you have an oasis in the desert, as long as that water stays there, it can get hotter and hotter and hotter, but these are plants that are adapted to hot conditions as long as they have water. So the idea there is that there are some locations on the landscape that are stable. And it's a very attractive idea. It's a very alluring idea, but I don't know, but we don't really know. Will it be stable when it's hotter? There's still water, but it's going to be hotter. And then what if it dries out? All of a sudden, the place that was stable becomes, quite unstable. So one idea has been really thinking about, are there places that are more stable that if we protect them, and now we get to the conservation, if we protect them, we protect a site that's going to, be resilient and the plants will hang on in the face of climate change. But what I'm arguing is that while something like a permanent water source might be stable, that this cool north-facing slope, there's nothing that, we don't know if there's anything that will keep it cooler. Like everything warms up. It's cooler than the rest of the landscape, but there may be nothing that keeps it from getting warmer. And there's a very, I'm going to use an analogy here, which is almost cartoonish, but it kind of makes the point. The ice floe is a refuge for that polar bear until it melts, which is to say, some of the things we're thinking about as refugia might just be the last place that species hang on, but they're actually quite vulnerable. They might not hang on for long. Whereas these species like on a south-facing slope that we wouldn't even think of as being, like we think of as being hot and exposed, it's like, well, maybe that's the population that really has a future here. So to a certain extent, I think this flips our thinking a little bit as we think about conservation, maybe, depending on how you think about conservation. Now, I'm going to unpack this in one more way before we wrap up this module. So we've also thought about this in terms of how species move on landscapes, okay? So we'll go back to this photo. I've made the argument here to you that this chamise here has a bright future under climate change because it likes hot conditions, and as it gets hotter, it could spread and occupy more of the landscape. Whereas these trees down in this north-facing slope are more threatened, and they're at the edge of their conditions, and if it gets a little bit hotter, especially if the water dries up, they would be quite vulnerable. And of course, this is a different version of what we see when we see trees dying. So if these species are doing better and it gets hotter, what we're saying is that they can basically expand. They're restricted to that warm site now, but they'll be able to move and expand. And when we go back to that dispersal idea, the important thing here is when we talked about dispersing a kilometer or 10 kilometers per year, right? 100 kilometers per decade, this is only 100 meters. So microclimates provide this and potentially this enormous resilience because the distances are so short. And this is where a lot of us have really focused our attention on the value of these rugged landscapes for at least some of the biodiversity, not all of it, not necessarily these species, but that, you know, in the face of these potentially long distances, these rugged landscapes provide a lot more potential for species to move around at a finer scale. Now, the flip side is what happens, you know, where do these trees go? So we've introduced what we call the outbound. We've introduced the ideas of outbound and inbound, just like you're at an airport. So under climate change, some species are outbound. Like this is no longer going to be suitable. So where are they going to go, or where will they be surviving? And what we're saying is that the outbound velocity for this species is really quite short. All it has to do is pop across the landscape. The outbound velocity for this one is, you know, where is the next place that's cool enough? And it could be quite far away. The flip side is when we think about something we call inbound velocity or an inbound distance. How far will a plant have to travel from to arrive at a site under future climates? Now we reverse it. For this site, the inbound velocity is quite short because the plants can just come from across the valley. But what if this hot south-facing slope actually gets even too hot for chamise? Where in the world does the next thing come from? So some of these hot adapted plants may do better because they can move across the landscape as it warms up further. But if these sites start getting too hot or dry for any of the species in the current landscape, the inbound velocities are enormous. And sometimes we, like when you come down the Sierra Nevada slope, you have the mixed conifer, you have, you know, maybe some oaks, and then you have the chaparral, then you get to the blue oaks, and then you get to the grassland. Well, what if you wanted trees? There's nothing there after the blue oaks. So when you get to that hot edge, that inbound velocity, where would you find something? You know, it may have to come from hundreds of miles away. So just a final thought as we wrap up. Part of this whole way of thinking in my research group and my collaborators has been that historically conservation biology has really focused on a species-based problem, endangered species. What's going to happen to that species? But if you're a land manager, you're charged with managing a landscape and a park, and you have to think about what's going to happen to my park. So partly this thinking about outbound and inbound has really been trying to be sort of symmetrical and thinking about if you're worried about a place, you need to think about what's coming. If you're worried about a species, you might need to worry about where it's going. And we need to be thinking in both ways, depending on the kind of conservation situation we're in, and whether it's more of a species-based concern or more of a landscape conservation as a park manager, an open space manager is dealing with, where their job is to take care of this landscape into the future, even as climate changes. And that will wrap up this module of our workshop.